Welcome to the UW Robotics Colloquium. It's my greatest pleasure to introduce today's speaker, my friend Nick Roy. Nick is faculty at MIT CSAIL in the Aero-Astro department. Nick and we met in 1998, quite a while ago, when he just started his PhD at CMU and I started a postdoc, and we both worked on the museum tour guide project, and Nick focused a bit more on, also during his thesis, on planning and decision making under uncertainty. Some of you might have heard of coastal navigation. That was kind of the first paper that we actually also worked together on, right, in the museum. And Nick, what's really great about his work that he also he cares about building robot systems that really work. So after the museum project, he was the lead student on the NurseBot project, which is building a mobile robot that you can send into a nursing home and it would interact with elderly people. And they also did not shy away from doing some real user studies. And Nick also leveraged his work on this kind of decision making and uncertainty for developing a POMDP-based dialogue system so that you could talk to the robot and it could ask adequate questions. And then at Aero-Astro, of course, he started working on quadrotors as well, where it's about, of course, again, planning, but also a lot of work on just 3D mapping of this environment. I remember he was the first who was able to put one of the depth cameras that we got our hands on, to put it on the quadcopter and then do some real 3D mapping with the Kinect camera. And besides just kind of the, let's say, the navigation aspects and mapping aspect, what I really like about the work is his work on language grounding, where I think he and his collaborators and team have done the very best work in the area, where it's about how you can tell the robot what to do. Nick's team, they showed how to command, for example, a forklift, what kind of task it should execute. And he's done some really cool follow-up work in that area. And as we all know, this is gonna be, I think, a very important area moving forward. Like, how can we interface with these robots? And Nick is clearly one of the leaders there. Also, as I mentioned last week already, I think representations is, of course, a big open question still in robotics, especially now with deep learning methodologies coming on board. And today, Nick is going to tell us his thoughts about hierarchy, abstractions, and geometry. And with that, I'll hand over to him.
Thank you, Dieter. That was really kind introduction. Ironically, I think that the things I'm going to talk about today lie in the null space of everything that you mentioned. And it's true. In 1998, it's nearly our silver anniversary. We got 2 more years to go. Anyway, it's a real pleasure to always come back to University of Washington and give a talk. And I'm just sorry it's not in person, because it's always really fun to chat in person with everybody there. So today what I want to talk about is sort of a research direction I've been pursuing for a little while, mostly because how our robots work kind of annoys me and continues to annoy me. So let me begin with this video here. This is from a DARPA program that ended a couple of years ago called Fast Lightweight Autonomy. And the idea was that we wanted to have a drone fly as quickly as possible through this urban environment and map the environment and also identify objects of interest. In this case, it's identifying and localizing all the cars while traveling up to 6 or 7 meters per second. And the top speed is actually limited by the physics of the vehicle, not by necessarily our algorithms. And the robot, as you can see here, is doing a reasonably good job. You see it's building a relatively sparse but useful map of the environment. It's identifying the cars and things like this. This is a military program. You might think about the military applications, but actually a lot of insurance companies have expressed interest in being able to very quickly localize all the cars in an environment after a natural disaster, like a city flood or something like that. So this was, a very satisfying program to work on in many respects, but there was one thing that really did and has continued to bother me about how our robots work, especially in terms of the control architecture. And some of you may have heard me talk about this before, because this has been a problem for a little while. Let's look at the base level autonomy for our vehicles just moving through the environment. You know, pretty much every operational robot on the planet has an internal architecture that looks something like this, where you have sensors feeding sensor data to an estimator that's maybe estimating the position. Maybe it's also doing SLAM in order to map the environment. And then it gives that point estimate to the motion planner. And the motion planner takes the estimate of the vehicle pose, let's say, and constructs a motion plan to the goal, feeds that as a reference trajectory to the controller, and then the controller gives motor commands. And this works very well. We wouldn't have drones, we wouldn't have robot arms, we wouldn't have uh, self-driving cars if this didn't work. And it runs at a fast duty cycle, and it runs robustly. But it's really only good for getting the robot from point A to point B in the configuration space. If we wanted to do a more complicated task, we want to do assembly, we want to do passenger pickup and drop off, we want to do package delivery from our drones, we need a higher level of autonomy. And pretty much every operational robot on the planet has, on top of that fast duty cycle motion execution loop, it has something like a symbolic planner that does things like sequences tasks. It takes the current state estimate, figures out where we are, maybe like it identifies what road segment we're on, or if we're a service robot indoors, it identifies what room we're in, what part of the task sequence we're supposed to be executing. And then it computes a symbolic plan that's usually given as a sub goal down to the motion planner, that does things like go to this street address, go to this room, pick up that object, and so on and so forth. And this doesn't have to run as fast. It runs at a much slower duty cycle, but also it is the case that this is the thing that often breaks our heart as roboticists. It's the thing that doesn't quite work right in terms of actually executing a task. Whenever we have human supervision, we're not supervising the motion planner, we're supervising what does the robot think it's doing next. So what is it about this architecture that gives us this lack of robustness and this brittleness? Well, inside each one of these arrows, there's information flow, and that information flow is conditioned on a model. The motion plan is conditioned not only on knowing where the robot is, but also having a map of the world. The controller is conditioned not only on having a reference trajectory, but also having a model of the plant, so that you don't ask the robot to do something that its motors can't physically do, or that it's going to cause it to oscillate or something like that. Now, where does each one of these models come from? Well, they're usually learned by data. So why don't I circle every arrow on this figure where I can learn the model by data? And so I can use system identification to learn a model of my sensors. I can use system identification to learn a model of my motors, so I can give stable motion commands. I can, have a map that tells the motion planner what to do. And I can also have a model of the kinematic and dynamic constraints, so the motion planner doesn't give a reference trajectory that the controller can't execute. I can even learn a model of I can use reinforcement learning, for instance, to learn a model of what are the symbolic actions that I should take given my current symbolic state. And what's really good about models that are learned from data is that they're generally robust. They're generally actually characterize the capabilities of our plant, the capabilities of our sensor, what we really want out of the robot in terms of executing high-level plans. But notice that I couldn't circle every arrow in green. And what that means is that there's some models that I can't learn from data. It's this relationship between the low-level physics of the vehicle, the low-level geometry, and the high-level symbolic plan, the sequencing that we want out of the system. So if we can't learn them from data, what do we do? Well, typically what happens is that we get a grad student or an engineer to come in and hand code. What does it mean to be inside a room? What does it mean to be on a road segment? How do I turn a symbolic plan of go pick up the object into an actual sub goal for the motion planner? And whenever we're hand coding things that we want a robot to do, we're building a ladder to the moon, right? We as people, there's lots of things that we can do really well, but it turns out that writing robot execution plans is not something that we're good at. And so what happens is this works until it doesn't work anymore. And we realize we forgot an edge case. So we realize the world has changed in some way that we need to update the model. And so we come in and write a new little snippet of C++ or Python. And then off we go. And that's a really poor way to do engineering, literally having a human do the optimization by hand. And this, just to be super clear, this is not a fanciful state of affairs. Dieter and I were on a Army project a few years ago, the robotics CTA, and this diagram here is the internal control architecture of that high level sort of symbolic planner. And we can zoom in a little bit here and look at what some of these high level actions are. So there's like a navigate action, which suggests we might need to go to a location. There's like a go observe. There's actual carry out a search pattern. And so these are high level actions that get given to the action executor, which then turns it into a motion plan. You'll notice that there are people's names under each of these things in the control architecture. When you've got a person's name in your control architecture, you've got a very, very brittle control architecture. Because like what happens if, as happened to us, that Bob decides he doesn't want to work for the Army program anymore. He wants to go and double his salary by going to work for Uber. All of a sudden, you no longer have somebody who's capable of maintaining your go-to action or your chain action, et cetera. So this is a problem, I think, for us as roboticists that we need to solve. Why is it that we actually have people's names in here? Why can't we actually learn these things from data? Well, the problem is that we don't actually have a statement of what is the learning problem. We don't have a statement of the objective function that leads to good symbolic representations. And so 2 questions that I really want to answer right now in my research group are, what makes a good symbolic representation, and how do we learn the relations between symbols and metric models? And that's really what I'm going to talk about for the rest of today, is what is a good symbolic representation, and how do we even define what it means for a symbolic representation to be good? Okay, so let's take that first question, is what makes a good symbolic representation? And I'm going to start with an extremely simple problem to think about that might tell us something about what are good symbolic representations. And one thing that I actually should be clear about is that I'm really standing on the shoulders of giants. A lot of my thinking has been informed by close collaboration with Leslie Kaelbling and Tomas Lozano Perez. In some sense, I'm playing catch up with them. I'm really bummed that Sid Srinivasan can't be here today. Because I know he's thought about a lot of these questions. This is sort of like my foray into this, informed by the fact that I just really want to deal with this problem of like, how do we optimize our entire system? So let's take a really simple problem. Let's imagine that we have 2 robots and they're constrained on a ring and they can't move through each other. So we have an R robot and an O robot. And so these 2 robots, by being constrained to be on a ring, a 2-dimensional ring, the joint configuration space is 2 dimensions. We have the position of the R robot on the x-axis and the position of the O robot on the y-axis. And together right now they occupy this point here. And let us imagine that we wanted them to change places. And so this is a motion planning problem like any other, but it's a really easy one. There's 2 solutions. They can either, the O robot can go here, and the R robot, because it can't move through the other robot, the R robot, it has to move over to here. So that's one solution. And we see the path in the configuration space is that the change in the y-axis is short because the O robot has a short path, and the change in the x-axis is a little longer because the R robot has a longer path to go all the way around. And these are rings, so there's wraparound from minus pi to pi. And the gray slash right here it would represent where the 2 robots are intersecting, and it's the disallowed part of the configuration space. It's what we call a collision, and the white part is the free space. And I said there's 2 solutions. The other solution is that the R robot could go this way and the O robot could go the other way around, and that would represent a path that went up and wrapped around over here like this. Okay, and it's an easy problem for us to solve. You can give it to your favorite motion planning system. On the left, you have just a regular RRT. On the right, you have RRT star, so it's optimizing, and absolutely no problem to solve this. So very good. Now, let's make the problem just slightly more complicated. Let us imagine that only one robot is actuated. It's the R robot, and the O robot is no longer actuated. It's an object. And configuration space doesn't change. If you actually, now the plan has to change because the O robot can't move by itself. So the R robot has to push the object into place. And so the plan now looks a little bit more complicated. The R robot has to push O over to here, and then the R, which is what's happening here, and then R has to come back here. Fine. And the plan in configuration space looks exactly like this. So, you know, the paths are now entirely horizontal, because this is when the robot is moving in free space. Until it's in contact with the object, it pushes it down the barrier of the free space and the collision space until it's in location, and then our robot moves back again. This relatively modest change to the problem does not appear to give us much difficulty in terms of expressing the plan. The plan isn't that much more complicated. But what's interesting about this is that your garden variety motion planner, RRT or RT star, is going to have a really, really hard time finding this problem. And why is that? And it's because it's now a hybrid system. And we have different modes of dynamics. We have the mode of dynamics where a robot is free to move around and the object doesn't move. And then we have the mode of dynamics where the two robots are in contact and the robot can push the object. And so we have actually a system that is analytic, in the sense the dynamics are smooth, except that the entire system is a composition of 3 piecewise analytic systems. And what that means is that an awful lot of our motion planning systems have a really, really hard time with piecewise analytic systems. Motion planners are very, very good at finding plans when this entire system is analytic. That's motion planning. And what we typically have to do is, or actually should say that, like, you know, there's lots and lots of problem domains have this property. And we can recognize that a problem is piecewise analytic when we write the dynamics that look like this. We have, like, for instance, in our dynamics function, we have a giant series of ifs that describe each of the different modes. And if we're not switching between those, then we generally assume they're smooth and analytic. Lots of problems have this property, that, like, object rearrangement, legged locomotion, and so on. And how do we solve these? We typically solve them as task and motion planning problems. And when we're in the land of task and motion planning problems, we typically give up on typically give up on optimizing, excuse me, with a small number of exceptions. And we typically end up on satisficing. And that satisficing is good because it makes it easy for us to write those high-level symbolic action state descriptions and symbolic action plans, and we just want the robot to try and get to the goal. But that's where a lot of my dissatisfaction comes from, is that we don't have a statement of what is a good breakdown of a task and motion planning problem that allows us to A, provide completeness guarantees, and B, provide optimality. But if we recognize that we explicitly have these 3 modes of dynamics, then maybe we can actually think about what do we actually how can we actually solve this in a way that allows us to provide, say, for instance, completeness guarantees. Maybe it even allows us to decide if the problem is solvable or not. And so the first thing I'm going to say is that we're going to define this notion of orbits. So an orbit is a set of states on a given analytic mode that is reachable without leaving that mode. And so connecting points on different orbits may require switching modes. So I have an analytic mode of the robot being in free space, but the robot can only slide back and forth along the ring. It can't actually move from horizontal orbit to horizontal orbit without actually moving the object as well. So if I want to switch from, say, this orbit here to this orbit down here, I have to basically move through this mode as well, where I'm moving the object. And so the idea of actually being able to solve these plans is that I need to, if I want to be able to move, if I want to ensure completeness of my motion planning strategy, then what I need to do is actually need to make sure that I am sampling from different orbits. And I need to make sure that my sampler actually covers my ability to move from orbit to orbit on the mode. Sorry, I missaid that. Let me say that statement again. Is I need to make sure my sampler covers all my analytic modes. And I need to make sure that my sampler actually guarantees that I can get from orbit to orbit on the mode. Okay, so how are we going to do that? Well, we're going to assume that we have a random sampling motion planner. And we're going to, what random sampling motion planners are good at is, given a particular analytic mode with an orbit, they'll cover all the samples on that mode. Or cover, so they'll give us good coverage of the orbits on that mode. So we just generate samples from the interior of the orbits. But the other thing that we saw is that if we want to switch from orbit to orbit, we better make sure that we're sampling those switch points from orbit to adjacent modes. And then what we can do is we can create an edge between any two configurations in the same orbit that's closer than a critical distance. And this distance here is fearsome looking. I'm not going to get into it, but it turns, if you know motion planning, then you know that you know about the PRM star and the RT star. And essentially what the PRM star and the RT star basically say that you have to sample, make sure your samples are putting edges between samples with some shrinking distance. And I'm going to compare, this distance is not exactly the same that we're shrinking the samples from the RT star or the PRM star. This is the distance that we shrink as we add edges in our graph from the RT star and PRM star. Notice that we just have a factor of 2 difference right here in order, as we're connecting edges between samples along our orbits and along our modes. And then we're going to basically expand our vertices by adding new orbits and then doing A-star expansions. So we sample on orbits. We require our sampler to ensure that we have samples on the connections between every orbit and adjacent modes. And then we just do regular A-star. What does this look like in practice? So let's go back to our really simple robot and object on a ring. And I'm just going to sample from the configuration spaces I normally do. And I'm going to notice that those samples are going to lie on orbits. And I'm going to make, for any orbit that I find, I'm going to make sure that I add a sample to adjacent modes, which basically puts me on the contact plane of the robot and the object. And then I basically can put edges between these points that join the these two orbits in the free space, and this guarantees that I'm going to be able to find trajectories that get me from the being in contact to not in contact. And that's the thing that's really hard for motion planning algorithms. The reason that we need task and motion planning algorithms is that we need to be able to plan through contact. Motion planning algorithms have a really, really hard time a lot of the time. Not true for all motion planning algorithms, but most motion planning algorithms have a really, really hard time planning through through that contact. And so what we've done by explicitly breaking our space up into orbits and being smart about how we sample is that we've given ourselves the ability to find those places where task and motion planning algorithms basically require you to have a symbol in terms of be in contact, get a grasp, open a door, move between rooms and things like that. So this sampling algorithm is complete. It's relatively inefficient, and we can do some clever tricks in terms of how we actually factor sampling, the positions of the robots versus positions of the object. This is a slightly more organized graph that allows us to actually solve this problem a little bit more efficiently. And so now we can solve problems like this task, what would seem to be a task and motion planning problem of like, how do I put the pink object into this space over here. If we give it to a task and motion planning problem, a lot of the time, that task and motion planning problem is actually going to solve the problem suboptimally by just saying, well, I can grasp the pink object and I can put it in the goal region here in essentially 2 steps. From a task and motion planning problem, that's the shortest path because it's the shortest number of tasks. If I give it to my new motion planning problem that actually understands how to move between these different contact relations and actually guarantee coverage of all the different analytic modes, then we find a near optimal path that is longer in terms of the number of tasks because I have to first move the object out of the way, but it's shorter in terms of overall task and shorter in terms of overall actual execution time. The reason I have near optimal path is because we're still subject to the same guarantees of stochastic motion planning optimality. It's optimal in the limit of infinite number of samples. For finite number of samples, it's near optimal. And Sertaç Karaman and Emilio Frizzoli told us how to actually bound those samples. So good. Have I solved the problem of where do symbols come from? I have not, but what I have done is I've said that, look, symbols are clearly related to these transitions between analytic modes in our dynamic system. And I observed that if we that if we were worried about completeness of symbolic representations, if we didn't want to have to actually hand code all the possible symbols that we need in order to complete these tasks, can we derive them automatically? And I've said that yes, we can maybe avoid the lack of completeness and avoid suboptimality by actually taking advantage of, like, how our dynamics factor. So maybe that's a good source of symbols. So a question you might ask is, like, given what I've just done, is there a definition of task and motion planning that is decidable yet expansive enough to be useful? And here we're going to do a little bit of a segue to just say, yeah, we actually do have an answer to the question of, can we at least, given our dependence on the dynamics, if we accept the fact that we have piecewise analytic dynamics, does that allow us to say whether any given task and motion planning problem is solvable? And the answer is that if there's a stratification, which I'll explain in a second, that is compatible with task and motion planning instance, then in fact we can decide whether or not the plan exists. And I'm very satisfied by this result, because what it does is allows us to say if we have dynamic piecewise analytic dynamics, and if the way that we're going to put those piecewise analytic dynamics into our motion planning problem by sampling on them, does that guarantee that we're going to be complete? Does it guarantee that we're going to be able to find a plan if one exists? And the answer is yes. And how does this work? I'm going to define a stratification as the partition of our configuration space into open pieces of constant dimension. So, we might have a configuration space that has some boundaries. And so we have, or a place where, our dynamics are piecewise analytic. And I'm going to separate the configuration space into places where we can move around freely in two-dimension space. I'm going to separate it into these boundaries where we can only move up and down because we're on the boundary. And I'm going to separate it into these points where we have a choice of going up and down, left, right, or moving into the place where we have smooth 2D configuration. So I'm going to assert that a stratification is a partition of a space into open pieces of constant dimension, just as the piecewise analytic dimensions of the robot and the object in the ring were piecewise analytic. We were either horizontal lines or we were diagonal lines, but they were lines of constant dimension. And I'm going to say that the control system is accessible if that entire stratification is essentially reachable. If I can drive, there's no gaps inside that stratification. So if it's the case that my dynamics are such that I broke up the space badly and I had a gap in the middle here that I actually couldn't get from this side of my orbit or mode to this side of the orbit mode, then I would either need to treat them as two separate stratification, or I would say the system isn't inaccessible. Our system is inaccessible. So I really want, like, as if I'm going to break the configuration space up into these chunks of dynamics, I can't have any gaps in my ability to move around inside those chunks. If I have gaps, I need to break it up in a different way. And I also need those chunks to be of some finite size. I can't have chunks that are vanishingly small relative to dimension. So I'm going to say they're uniformly accessible if there's a minimum size on each one of those chunks. And here's an example of a discretization that is not uniformly accessible, in that, like, I'm breaking this space up into vanishingly smaller balls. And so the proof that we have is that if the system has uniform stratified accessibility, which means that I'm going to discretize my world into pieces that are of minimum bounded size, and I'm going to break up the world into break up those chunks into such that my dynamics allow me to basically access any part of the inside of that region. Then that's a good representation that essentially I can move around inside that space. And the really nice thing is that we showed that there is an algorithm that allows us to prove whether or not given a planned problem that we want to solve inside there, we can prove whether or not a solution actually exists. We can't decide if the model is correct, but we can in fact tell if it's broken. Is that if you give me a motion planning domain, and I look at the dynamics and I say, okay, I'm going to break the dynamics up into piecewise analytic pieces. And so long as those piecewise analytic pieces are complete in the sense that they're accessible, there are no gaps where I can't go. And so long as those pieces are of finite bounded size, I can now decide whether or not whether or not I can solve that planning problem for you. Any planning problem, I can tell you in, some complexity. You see the complexity here, whether or not I can solve that. So that feels like now a statement about what makes a good symbolic representation. Is a good symbolic representation is one where the decompositions are uniformly accessible and have piecewise analytic dynamics. So there's some hairy algebraic topology that's gone into working this out, and this is work with my former grad student Will Vega Brown. We're really pleased that we actually started. Algebraic topology may give us a way to actually decide whether or not it doesn't allow us to automatically derive uniformly accessible striations, but it allows us to know if our representation is good. One problem. So why do we like symbolic representations? Why do we like these abstractions? We like them because they give us computational tractability. The way that we solve any hairy computational problem in computer science is we induce abstractions of one kind or another. And so the algorithm I just described and this notion of sampling on our orbits and making sure that the orbits are connected to neighboring nodes, and then the proof that says that if you do that and that your orbits and modes are uniformly accessible, then the problem is decidable. It didn't buy us any computational tractability. So Will actually took some of the problems that we were looking at and just gave them both to his algorithm, which is the fast orbital Bellman tree algorithm here, and also gave it to a bog standard task and motion planning problem here. What you see is that the task and motion planning problem is finding plans. They're not as good as Will's planner, but he's also finding the bog standard task and motion planning algorithm is finding them in 1 to 2 orders of magnitude faster. So that's bad news for us. We find good plans, but we find them really, really slowly. And that is because although we had a good, representation that ensured completeness and allowed us to optimize the task and motion planning problem as a motion planning problem, it didn't admit any kind of abstraction at all. And so how do we actually get to adding abstractions? Well, let's think about how we actually solve these search problems. Really what the orbital Bellman tree algorithm was doing, and the sampling and striations, was finding a good representation, but it wasn't helping the search process at all. How do we help the search process? Well, we typically inject domain knowledge in the form of heuristics. And let's imagine that I'm trying to get to the goal location over here. Then, typical heuristic that we might use is the shortest path heuristic that you see here. And so if we look at what happens with the search tree, the search tree ends up exploring, reasonably. It starts making progress to the goal, but it doesn't realize that it's not going to be able to actually get to the goal through this door, through this wall here. And so the heuristic that we gave it didn't really help all that much. The heuristic started to help quite a bit once we got out of these sequences rooms over here. But it didn't do the right thing. And really, the Euclidean heuristic is a local heuristic. It knows sort of where the goal is, so it's global, but it uses really local information to make progress towards the goal. It doesn't actually have information about the global structure of the space. And when we have things like non-convex obstacles, then it gets problematic. So how can we actually induce both local and global heuristics? How can we use local and global heuristics to derive an abstraction that might actually help us, solve these problems? So the initial sort of notion of orbits and modes gave us completeness and optimality, but it didn't give us efficiency. Where can we get efficiency from? And Stuart Russell and his postdoc, PhD student Bhaskara Marty in 2008 had this idea of angelic semantics. So the idea of angelic semantics is that you can bound the cost of any primitive plan using abstract operators if the abstract operator actually gives you both lower and upper bounds. So lower bounds might be great inside the search derived from local information, but global upper bounds really require you to know something globally about the structure of the space. so that is where abstraction can really help us, because abstraction is not going to give us the total answer in terms of the total cost of the plan to the goal, but it's going to give us some information about the total cost of the plan to the goal, and it's going to allow us to compare different directions. And so the idea of angelic semantics is you have these valuations that give you, both a lower bound here, but also a bound on the upper bound of the cost to get between sets of states. So this might be a lower bound, and then this might be an upper bound in terms of the cost of from one state to another state. And the cost bounds really encode information about abstract operators. So if the cost function is an arc length, then the Euclidean distance is a great lower bound. If the abstract operator is restricted to a convex set, then there's ways to actually get good upper bounds as well. So if you need to know something about that convex set, but here's a really simple upper bound between 2 points in a state space, and this again comes from algebraic topology and is a kind of surprising upper bound. There are other ways that you can get upper bounds as well. So connectivity and topology can lead to bounds. If two regions are disconnected, then there's no plan with finite cost connecting them. And so if you think about this diagram here, man, it would have been great to know that these two this straight line path between the start and the goal is essentially disconnected. The topology between the start and the goal here is disconnected, and the topology, if you move this way to the goal, is connected. That would be a great way to actually compare whether or not the heuristics over here are useful compared to the heuristics over here. And so without going into the guts of the algorithm, if you actually use an abstract representation of this, I'm getting ahead of myself. But if we use an abstract representation of just the connectedness of the room, we extract a topology between these rooms, and we use that to derive upper and lower bounds. If you compare what the corresponding algorithm does, that actually prunes away parts of the state space where the lower bound of the heuristic is higher than the upper bound of some other path, then you can basically prune away those parts where the lower bound isn't useful. And we get much more efficient search here, guided by the abstraction. And so hopefully this is very satisfying to you all, that by essentially recognizing that the lower bound over here is going to be worse than the upper bound over here, we get very, very efficient search. But it's better than that in the sense that we can even combine discrete variables as part of our search process. So let's imagine that we have a planning problem here where we have to get to the goal, and we have doors that we need to get through. So those are discrete part of a configuration space. And the switches for the corresponding doors are in these green locations here. So this green switch here opens door 1, this green switch here 2 opens door 2, etc. If you give this to a standard motion task and motion planning problem, it's going to recognize that you need to open the doors in order. So you figure out what is the order of the doors, what is the order of the switches, and then you just go and open switches flip the switches one after another until you can find your way to the goal here. The problem with that approach to task and motion planning is that you can actually do better than that if you actually incorporate the upper and lower bounds for planning the full trajectory as a motion planning problem. So here's again, without getting into the guts of the algorithm, by actually taking advantage of our representation of the dynamics and then giving ourselves abstractions that allow us to actually prune away chunks of this search space, we can find a plan that actually goes first to this switch here and opens door 1, but then does not go to door 2, actually goes to door 3 next, opens the switch to opens door 2 switch on its way to opening another switch here, then finally gets to 5, and then gets to the goal. And the real thing is like, task and motion planning can solve this problem, but can we solve it efficiently? And if you look at a comparison of like A star or weighted A star, you see that the computational complexity grows exponentially, by using abstractions that actually prune away the search space, then we can actually find these plans very, very efficiently. And so the best algorithm is this. So this is Angelic A star right here, which uses the upper and lower bounds to prune away the search space. And then these are, additional algorithms that that have extra tricks to pruning away more of the search space using more of the abstraction. But the point is that we're expanding many, many fewer states, and we're expanding many, many fewer plans, and we find good plans efficiently. Now, this is all about kinematic planning. Even when I had the robot that was the ring and the robot and object on a ring, I wasn't really taking into account true dynamics. I wasn't worrying about forces and torques. I was worrying about differential constraints, which we often think of about dynamics. But what happens if we actually have a robot that has true dynamics? So this is joint work with Dan Kodachek and his student Vasilis Vasilopoulos at Penn. And this is the Minotaur. And the way the Minotaur works, and I'll play a video in a second, is it's basically bounding in place. And it's not like Boston Dynamics Little Dog, which has static stability and actually like moves one foot at a time. This robot really, you have to worry about the dynamics and the torques in order to get it to not just navigate, but move things around. And so the question is, can we, at this point, we can no longer solve this problem as a traditional task and motion planning problem, because task and motion planning typically focuses only on kinematic constraints. And we have real dynamic constraints in here. And so what Dan and Vasilis had developed was a low-level controller that was capable of executing certain kinds of navigation plans in environments without having to solve a full motion planning problem. But they could really only make the robot move from place to place, and maybe they could get it to push things. So they couldn't carry out really complicated plans. So for instance, oops. Could you actually have the robot do the kind of box pushing that I showed you a few slides ago? Could the robot actually, move these objects around in order to satisfy some particular goal by sequencing Vasilis's controller? And the question now changes in terms of, have you got the correct stratification of your space? Have you ensured that you put your motion plans or your motion samples such that you can transition from mode to mode? Now the question is, what are the guarantees that the low-level motion planner can provide Vasilis's reactive controller to the high-level planner such that you guarantee completeness and some measure of optimality? And without getting into the details of the algorithm, this is just some stupid robot trick videos. But what we were able to do is that we were able to show that we were able to solve these complicated dynamic task and motion planning problems relatively efficiently. On the left, you see the robot actually move the table into place, and then it's able to leap from step to step in order to get to the goal configuration of over here. And then the video over here showed Minotaur. I'll play the video on the right again. The video here is the Minotaur is able to leap onto the stool. It's able to use its funky gait in order to push the object out of the way, and then it's able to navigate its way to the goal location, which is over here. Even better, the high-level planner doesn't even necessarily need full access to the geometry of the space. The robot's actually able to by virtue of Vasilis's low-level controller, we can actually introduce convex objects into the space that the low-level controller is able to steer around and preserve optimality and completeness. And I want to be a little bit careful about optimality because, again, it's near optimality, limited infinite samples, etc. So, and then, by virtue of being able to have Vasilis's controller able to solve big chunks of the underlying motion planning problem very efficiently, we're able to solve those planning problems very, very efficiently. So that, we're, not seeing the exponential growth of baseline planners. Our hierarchical planner built on top of the controller is able to solve these plans really efficiently. So, my question was, what makes a good symbolic representation? And the answer, is that decompositions into symbolic pieces that are uniformly accessible, piecewise analytic. And maybe another answer is that we have good upper and lower bounds, and maybe another answer is we can make a contract with the controller. We had a contract that with the ring and robot and object on a ring that said that, well, I need the motion planner to sample from the boundaries between the orbits and the adjacent modes. With the Minotaur example, the contract is a little bit more complicated, and we have a RSS paper under review that lays that out. So in the last few minutes that I have here, the last thing I wanted to say is, okay, so how do we learn can we learn these relationships between symbols and the metric models? So it is the case that what I've talked about before really assumes that we have a perfect model ahead of time, and that we can do these complicated algebraic topology calculations that allows us to break up the planning space or the planning model into pieces that allows us to preserve these guarantees. If we have perception in the system, then can we do something a little bit better? And the question is like, if we're using our perception system to build a map, then what kind of map are we building? We typically build geometric maps, and the maps do lots of things for us. They allow us to compute some terms of the Bellman equation in order to do path planning and optimization of trajectory. Certainly, the maps allow us to avoid local obstacles, and they allow us to divide up our action space into striations. There's a bunch of work that my group has done in terms of using other different kinds of maps that allow us to actually plan efficiently without having to do this kind of geometry. And I'm going to skip ahead a little bit to show a case where if your perception system doesn't necessarily give you perfect geometry, but actually gives you discontinuities in the world, then can you still actually build a map that's useful for planning? And this is an example where the robot's driving around and building a geometric map without from a very, very rudimentary sensor that's actually just observing discontinuities in the world. And I want to advance this video. Here we go. Yeah, this is the robot driving around in a building at MIT campus, where you see it's extracting just the boundaries between free space and obstacle space, and it's actually able to recover from the single camera where it's learned to predict the boundaries of the free space and configuration space, and it's actually able to recover this geometric map. So this is all by way of saying there seems to be something very special about discontinuities in the world, both in terms of discontinuities in your dynamics, but also discontinuities in your perception. And if I had more time, I'd sort of talk a little bit more about this work. But the point is that, okay, if we can get a geometric map out of a single forward-facing camera by extracting the just the discontinuities in the range, there's a lot more information in these images that maybe could be useful. And the last thing I just want to touch on is that perception actually gives us non-geometric information, what a lot of the time people call semantics. So, you can do object recognition, and you can project those objects into the maps that you might have, and you can use that information to actually make useful predictions about where your plans might be. So maybe good symbols like windows and doors and exit signs, maybe those symbols are actually useful for actually making predictions about where good plans might be. I'm not necessarily going to have perfect, if I have an object detector for windows and doors, I'm not necessarily going to be able to localize them perfectly in my map, but maybe I can train a system to actually predict where good plans might be from that non-geometric information, those symbols. And this video here is an example of a robot navigating through an environment where we take, object detection bounding, I think, ellipsoids. Yeah, there we go. So we have an object detector. We take those detected objects and we plunk them into the map over here, but in a very non-geometrically faithful way. You notice that we're not building a door into the map, and we're using them to actually make predictions of the fact that this is a long hallway, and that maybe the robot should actually make more progress towards the goal by driving down the hallway, as opposed to getting distracted by perhaps errors in the map and imperfect geometry. So this is, again, this could be a whole other talk in terms of how we actually use symbolic perception to inform our planning. But the question a question that I think is still very unanswered is like, how do we learn the relations between symbolic and metric models? The best answer I have so far is that symbolic representations might be good for identifying discontinuities that help us build better maps, or they might be good for learning relations between what our plans need to look like and what we're seeing out there in the world. And then one more question that I haven't answered, which I think is really, really important, is how do we acquire new symbols? So everything that I've talked about is predicated on having a knowledge of what are either our perceptual symbols, our objects in the environment. It's predicated on having a model of the environment that we or the planning domain that we can then break up into these pieces of piecewise analytic domains or into the uniformly accessible striations. But if I enter a new domain and I need to build a domain from scratch, how do I actually get new symbols? How do I learn new objects? How do I learn new perceptual properties of the objects? This, I think, is a hugely open question that, very, very few people are tackling. And so really what I want is a new mathematical theory of representation that allows joint inference over the continuous physical world and discrete concepts in a principled fashion that allows us to learn representations that correspond to the structure of the physical world and the human understanding of the world. Dieter made mention of the work that we had done in natural language grounding, and if we can acquire new symbols and we can attach language to it, then that would seem to be very powerful. And then something else that I haven't talked about at all is uncertainty. Is how do we attach uncertainty to symbols as we're acquiring them? So I think there's a whole space of hybrid representation theory that is very much open for inquiry that I'm excited about trying to examine. So, of course, a great group of students that have helped with a lot of this. Dan Kodacek at Penn and his student Vasilis have been great collaborators and had tremendous support from a number of different organizations that's enabled a lot of this work. So hopefully I've given you a sense of the kinds of things that we're trying to tackle in my group, and I'm happy to stop here and take the questions you might have, and thanks very much to all of you for inviting me to be here.
I had a question, if I can, or maybe a more comment, but
yes.
So this thing you're mentioning about the relation between discontinuities and symbolic representations, which in your examples is more about space. I'm thinking there's an analog for it in the time domain with like states and events. And the thing, and also its connection to language. So the thing I've noticed with the baby at home is a lot of our language kind of correlates with state changes or events, and that's kind of a more natural thing to correlate. Like there's sort of an unsupervised signal of something changing, which brings attention to a few things versus, if I was just using language to label a state, there's like everything that's currently true is being labeled. So there's like, it feels easier that you would be learning to attach words to events as opposed to words to states or things. And infant directed speech sort of definitely takes advantage of this with like, things are not in the view and then suddenly they appear and you give a name to it, right? So there's like this burst of state change and a word that happens very close to it. So have you thought about like the same concept in the time dimension?
So that's an awesome observation, Maya. Thank you for that. And I would say, I am acutely aware that we've kind of ignored the dynamics of the environment in all of this work. And it's a huge gap in the kinds of things that we're thinking about. And I would say that like events correspond to discontinuities in time in the dynamics, and the same idea holds, is that like, I do think that there is absolutely a way to attach a meaning or semantics to when things around the world change in ways that you didn't expect, or that it's discontinuous. There's something special about discontinuities that we're not leveraging in our algorithms right now, and I think that's a really great example.
I had a related question.
Please.
So building up from discontinuities in the dynamics is really fascinating, but as I was watching that, the question I had is, does that help or hurt our ability to use the symbols to make other things convenient? because it seems like part of the art of how we build symbols for robots is sometimes just to make it easier to ground language to those symbols, or easier to do some other application we're interested in.
Yeah, so that's a really good point. So I do think that it makes it easier, but not in the way that you mean. There's another step. So I've done of 3 or 4 things that need to happen in order to get like to a really mature form of hierarchical abstraction. You need to make sure that your base level representation is correct and complete. And I think I've shown that. And I have shown that if you have a hierarchical representation, if you attach upper and lower bounds to it, then you get computational efficiency. And that's the kind of thing that we like out of our representations. What I have not done is I have not shown how to take the base representation and turn it into a hierarchy of the kind that you want. And I've also not shown how to automatically derive the upper and lower bounds that give you the computational efficiency you want. So there's pieces. So I feel like I'm putting together a puzzle that when it's complete will give us a theory of hierarchical abstraction, but I don't have all the pieces in right now. And that's a really good example of one, is where, we're automatically constructing it in a way that makes things easier. What I've done, as I said, if you do it in this way, good things will happen, but I haven't given you a recipe for doing that. Great comment. Thanks for that.
So it seems like in your case, the symbols through this, and I have to read the paper for the details, but comes out of a very, let's say, deliberative process about how this world functions and how things are related, right? Could you imagine, and that's a little bit related maybe to also Maya's comment, that there's this, again, this other notion is more experience-based, right? You are doing in the real world and you are observing streams of sensor data and controls. And from those, you're trying to do more, let's say, a temporal spatial segmentation. And maybe that could be an alternative way of getting these symbols. Of course, I haven't seen a lot of work where that has succeeded. So I'm not saying that is, I just want to get your thoughts on these different approaches.
No, it's a great point. And the closest we have gotten to that is the work with Dan and his student and the low-level controller that they have. So that is a case where so the word deliberative is exactly right, Dieter, is that all of the hierarchical abstraction, I think, is deliberative and is sort of like starting to look like old school AI. And how do you square that with, modern machine learning and modern control, et cetera, which is very much not that. And so what we were able to do is ask Dan and Vasilis we gave them a contract and said, if you honor this contract, then we can sequence your controllers in a way that you can't sequence them right now in order to accomplish these higher level missions. So I think that there's an entire space of work to be done. And so let's say it wasn't a controller for Minotaur, but let's imagine that it was a learned controller for, I don't know, a self-driving car or a different kind of quadruped or something. But if you could learn a controller that adhered to our contracts, then we would get the benefit of that sort of learned behavior and smooth behavior, but you would get the benefit of our ability to tell you what to do next.
Mm-hmm.
And I am chewing at that. I don't have a way to write those contracts in general. Will had a paper at AAAI last year in 2020, which laid out a general theory of those contracts, but it was very divorced from the actual, anything that would make a robot really work. And it was it took Will and Vasilis, they nearly didn't make the RSS deadline, that even starting with an understanding of the theory of how to write these contracts, it took them a year and change to actually figure out how to write the contracts in the code to actually make the system work.
Awesome, thanks. Thanks everybody for joining, and Nick, of course, thanks for giving this excellent talk, and we'll have some more time to chat.
Yes, awesome.